Have you ever watched a movie and just thought, wow, that is absolutely incredible, but is there any way that could actually happen? Well, today we're doing exactly that. We're taking one of the most mind-bending ideas from a modern sci-fi classic, Interstellar, and we're going to see if the science actually holds up. You'll see how this impossible planet is actually a perfect way to understand some of the wildest, most profound truths about our universe.
I mean, it's one of the most unforgettable lines in the whole film, right? The crew lands on Miller's planet, this water world orbiting a giant black hole, and they realize every single hour they spend there, 7 times years are passing for everyone and everything they left behind. It's an absolutely heart-wrenching, high-stakes idea.
So, was that just a brilliant bit of writing to ramp up the drama? Or is that kind of extreme time-bending actually allowed by the laws of physics? That is the big question we are going to unpack today. And believe it or not, the answer lies in one of the greatest scientific ideas ever conceived.
Okay, let's dive right in. To really get our heads around Miller's planet, we first have to get our heads around Albert Einstein's view of the universe, and it all comes down to his groundbreaking theory of general relativity.
Now, you probably think of gravity as a force, right? Something pulling you down. Well, Einstein told us to throw that idea out. He said that space and time aren't two separate things. They're woven together into this single, four-dimensional fabric he called space-time. And really, really massive objects, like stars, planets, and especially black holes, literally bend and warp that fabric. What we feel as gravity is just us following the curves in space-time.
The best way to picture it is the classic trampoline analogy. Imagine you put a heavy bowling ball in the middle of a trampoline. It creates this deep dip, right? Now, if you roll a little marble nearby, it's not being pulled by the bowling ball. It's just following the curve that the ball created in the trampoline. That's gravity. In a nutshell, it's matter telling spacetime how to curve, and that curved spacetime telling matter how to move.
Okay, so here's the kicker. It's not just space that gets warped, it's time too. The deeper you go into one of those gravity wells, so the closer you get to a really massive object, the slower time itself actually flows for you compared to someone far away. And this isn't just a feeling. We're talking about your clock, your heartbeat, your entire aging process. Everything literally slows down. This is called gravitational time dilation.
All right, so now we've got the basic tools. Let's take this seriously mind-bending physics and apply it to the movie. We know Miller's planet is orbiting a supermassive black hole they call Gargantua, where gravity is almost unimaginably powerful.
And this is where we can stop just talking theory and actually do the math. Just how extreme does the situation need to be to get that unbelievable time difference, where 1 hour equals 7 whole years?
The number you get is just staggering. For 1 hour on Miller's planet to equal 7 years on Earth, time there has to be running more than 61,000 times slower. 61,000. To get that to happen, you have to be perched right on the very edge of one of the deepest gravitational wells in the entire universe. But here's where we hit a huge snag. If you do the math for the simplest type of black hole, one that isn't spinning, you find out that for the time dilation to be that extreme, the planet would have to be right at the event horizon. You know, the literal point of no return, where not even light can escape.
And that's the deal breaker. See, for a non-spinning black hole, the spot where you get that kind of time dilation is the event horizon. But physics tells us there's something called the innermost stable circular orbit, basically a minimum safe distance. Get any closer than that and you're just going to get sucked in. And as you can see, that stable orbit is way, way farther out than where the planet would need to be.
So based on this, it looks like the movie just got it wrong. A planet simply couldn't exist there. It would get torn to shreds or swallowed whole. It's a paradox. But what if we've been missing a key piece of the puzzle?
So how do we solve this thing? Well, the secret is spin. You see, not all black holes are just sitting there being boring. In fact, astronomers think most of them are probably spinning like crazy. And that changes everything.
When a massive black hole spins, it doesn't just spin in space. It twists and drags the very fabric of space-time around with it. Imagine a spinning mixer blade in a thick bowl of honey. It's kind of like that. This incredible effect is called frame dragging, and it completely rewrites the rules of gravity nearby.
So here's how it works. First, Gargantua is spinning at an incredible speed, close to the speed of light. Second, this insane rotation literally drags space-time along for the ride. And third, this frame dragging effect basically gives Miller's planet a little extra boost, a little extra support. It allows it to have a stable orbit in a place that would be completely forbidden around a non-spinning black hole. It can get right up close to the edge without falling in.
And just like that, the science works.
The filmmakers, who were actually advised by the brilliant physicist Kip Thorne, found a perfectly legitimate loophole in the laws of physics. By making Gargantua a rapidly spinning black hole, the impossible suddenly becomes possible. The planet can exist, the time dilation can be real. This is science fact.
Okay, so we've established the physics checks out, the planet's orbit is sound. But that just opens up an even cooler question. Even if the planet can be there, could anything possibly live there?
So now we're shifting gears a little, moving from general relativity into the world of astrobiology. I mean, what would it actually take for life to survive, let alone evolve, in one of the most violent extreme environments in the universe, right next to a cosmic monster?
Well, it would be this incredible balancing act. On the one hand, the swirling disk of hot gas around the black hole, the accretion disk, could act like a sun, giving off light and energy. The problem, that same disk would blast the planet with a constant storm of deadly X-ray radiation. Another option could be geothermal energy, caused by the black hole's gravity squeezing and stretching the planet. So maybe, just maybe, the only way for life to survive would be deep underwater or underground, shielded from that lethal radiation on the surface.
So, we started with a simple question from a sci-fi movie, and it took us on a journey through warped space-time, spinning black holes, and the absolute limits of where life could exist. So, after all that, what's the big lesson here?
I think the biggest takeaway is this. The actual laws of physics, as we understand them today, allow for realities that are so much weirder and more wonderful than anything we experience in our daily lives. Scenarios that feel like pure fantasy, like a world where an hour is 7 years, are actually tucked away inside our best scientific theories. It just goes to show you that sometimes the greatest thing science fiction can do is push our imaginations to the very edge of what's truly possible.